Welcome back, class. Today we are going to start our discussion of our two-chapter unit on chemical bonding. In this unit, we're going to be covering chapters 10 and 11 and dealing with various aspects of chemical bonding. So we're going to start off by looking at chapter 10, which is going to focus on the Lewis model, which is sort of our basic modeling process that we're going to use. And then as we go forward, we're going to expand upon Lewis theory and look at some alternatives to Lewis theory as well. Now, bonding theories in general, and Lewis theory in particular, right, try to explain how and why atoms attach and form molecules, right? So we have all of these molecules that form, and we want to try to explain why. Not only in sort of the simplest terms, like why does it happen, but in more sort of detail in terms of what do the structures look like, what do the bonds look like, what type of bonds, all these different kinds of things to try to explain why we have such an array of different compounds. We can also try to explain why some things don't form, right? Why are certain structures stable and other structures not stable? So, why is a neutral H2O molecule stable, but a neutral HO or H3O is not? And so we can try to answer, why some combinations form, why others don't. We will look at predicting three-dimensional geometries of molecules as we go forward. And, of course, we can use this information to try to predict properties, right? Why do molecules behave the way they do? Right? What is the link between structure and behavior? So, Lewis model is the first model we're going to look at, and it's going to be our base, right? We're going to spend by far the most time looking at Lewis theory, and it's sort of our go-to model. And in a lot of respects, it's a very simple model, right? Lewis theory. But in the same sense, it's an extremely effective for getting basic bonding and behavior information. And it is used by chemists all over the world to do basic modeling, even when more sophisticated modeling tools are available because of the time involved, right? Lewis structures can be drawn very quickly, and they can give you, nice starting point for basic information. Then if more detail is needed, right, you can work on other models. But what is this model premised on? Well, as we'll see, this model is all based around the valence electrons. Now, why the valence electrons? Well, remember, we've had some talk before about why the electrons and the valence electrons specifically are important. And that is, remember, these are those outer electrons, right? The electrons that are exposed within an atom. And these are the ones that are going to be available to bond, right? These are the ones that are going to be involved in bonding. They're going to be involved in the formation of ions, right? So these are really the key electrons in an atom. And so Lewis theory is based upon these valence electrons. Now, ultimately, we're going to draw what we call Lewis structures. And using the valence electrons and what we know about stable bonding to predict these Lewis structures. Now, some of you may know these as electron dot structures, right? Same thing, we represent the electrons as dots. And again, these are going to allow us to make predictions on properties of molecules. We'll ultimately be able to predict things like polarity, stability, of course, connectivity, which atoms are bonded and how to a certain extent. Now, of course, we'll also talk about a little bit later, why this isn't the most, perfect model, right? There are limitations to this model. Now, we'll start our discussion by looking at why do atoms bond, right? Why do we form compounds in general? So, of course, we know that we do because we know that they exist, and there are many, many, many substances throughout, the Earth, right? More so than the whatever, 90 some, 100 some now elements that are available, right? If they didn't form compounds, that's all we would have, right? And so clearly we know that bonds exist. The question is, why do they form? Now, ultimately, we'll go over these points, but ultimately, if you want to summarize this, bonds form because it lowers the potential energy. And as we've mentioned, and we will continue to mention, physical, chemical processes ultimately occur because we get to a more stable energy state, right? There's an energy component there. And so most of the processes that occur, if we want to predict why they occur, there's probably something in there that has to do with a lowering of energy or getting to a more stable energy state. Okay, so we lower the energy between the particles involved in the bonding. So what does that mean? Well, if we take individual atoms, of course, right, they have a certain potential energy. So there is something about bringing those atoms together to form a chemical bond that lowers the potential energy. So the energy of the bonded atoms is lower than if they were on their own, right? And more specifically, we think about the particles, the charged particles within the atoms that form these bonds. So this is ultimately going to be electrons, right? When we think about this, ultimately going to be electrons and protons, right? And we can sort of summarize protons by thinking of the nucleus, right? So these are the interactions that we're ultimately going to think about. So to look at these, right, we have to consider some different interactions, right? Of course, we have nucleus-nucleus repulsions, right? So, of course, as atoms come closer together, so if we visualize atoms as, say, we have these positively charged nuclei surrounded by some negatively charged electrons. As these atoms approach each other, of course, those positive protons, those nuclei, start to get closer and closer together. Ultimately, if they get too close, they will start to repel each other. So we're going to have to deal with repulsions. Well, of course, we're going to have to deal with electron-electron repulsions, right? As atoms get close together, electrons repel each other, right? They don't want to be close to each other. But ultimately, right, it's a balancing act between these repulsions and the attractions between the respective nucleuses and the electrons in the opposite atom, right? So as we bring these atoms together, while the electrons and the nucleuses repel each other, there is attractions between the electrons here and the nucleus here, right? So these start to attract each other, and then this nucleus and these electrons attract each other, and we pull the atom together. So it becomes this balancing act, right? So the atoms get close, but not too close, right? And ultimately this will result in bond lengths, right? The atoms are not as close as they can possibly be, right? There's an ideal distance that balances these repulsive and attractive forces. Okay, so a little bit about why atoms bond, and ultimately it comes to it's more stable. Now, types of bonding. Now, we first introduced these things back in Chapter 3, so you can look back there to get some information as well. But we're going to talk about 3 major bond types, and one of them we're not really going to talk about very much, and the other 2 we're going to talk about a little bit. So, we have first ionic bonds. This is the one that we've spent the most talking about. And ionic bonds form by a transfer of electrons. And we looked at this back in Chapter 3, where we have a metal and a non-metal coming together. So one thing to remember, right, is that metals have a high, let me rephrase that, have a low ionization energy. So they really want to lose electrons. In nonmetals, have a high, what we call electron affinity, meaning they want electrons, right? They want to gain electrons. And so we have this balance of metals that want to lose, nonmetals that want to gain. And so when you put a nonmetal and a metal together, we get a transfer of electrons and we form ions, right? Remember, our metals are going to form positive ions. Our nonmetals are going to form negative ions. And we're going to come together to form an ionic compound, right? Remember, ionic compounds exist as lattice structures, not as individual molecules. And so if you want to review some of this, again, chapter 3 is a good place to go. We have covalent bonding. This is the one that we're going to spend the most time on because, frankly, it's the most useful to us in terms of the types of molecules that we're going to be looking at. So we'll spend a little bit of time at the end of chapter 10 talking about ionics, but most of the time we'll be focused on covalent bonding. Now, covalent bonding involves the sharing of electrons. So because we have only nonmetals, right, and nonmetals have high electron affinity, but they have high ionization energies as well. Meaning they really don't want to lose electrons. And so you have these two nonmetals, they really don't want to lose it, even though maybe they want to gain it, but so they just end up sharing, right? We don't get a transfer, we get a sharing of electrons to form covalent bonds, right? So we have ionic and we have covalent. Now metallic, we're going to spend just a little bit of time at the very end talking about these, but we're really not going to focus too much on them. Okay, so we got our three major bond types. So a little bit more ionic bonds. Again, should be mostly review. When a metal loses an electron, it becomes a positive cation. When a non-metal atom gains an electron, it forms a negative anion. Right? Because again, metals have these low ionization energies, easy to remove electrons. Non-metals have good electron affinities. They really want those electrons. So we get a good combination, positive, and we form the ionic bond. And this results in our crystal lattice. Right, remember, no molecules here. We have covalent bonding, where non-metal atoms, because they have these high ionization energies, as I mentioned, we can't really remove electrons to them. You know, they don't like to form positive charges. So when they come together, they simply share because they both want to gain electrons, essentially. And so the way that we get around that is that we share valence electrons. And we'll see why this is advantageous in a little bit. And it turns out that that potential energy, right, the lowest is when those electrons are sort of localized, if you will, between the two atoms. So if we think about the negative charge being located between the two positive charges, and we can think about mutual attraction here. Right? So the electrons are mutually attracted to the two positive nuclei of the bonding atoms. Now, metallic bonding, again, this is one that we're not really going to look at too much that this is the kind of bonding we take place in bulk metals. So if we have a sample of iron or gold or whatever. So since metals have these low ionization energies, when they bond with other metals, right, again, not everything can lose electrons. Well, they can, and this is how we sort of think of it. But nobody really wants to gain them. And so the simplest theory involves what's called a sea or pool of electrons, where basically all of the metals lose their electrons, and we form a bunch of metal cations that we refer to as sort of islands, and they are surrounded by these electrons. And these electrons are what we call delocalized, meaning they can move throughout the structure, right? So they're not tied to any particular metal atom or metal ion at this point. They can free to move. And so we get attraction between the cations and the delocalized electrons. And this, as we'll talk about, right, makes some sense because based on the properties of metals and their ability to, say, conduct electricity, right, where electrons have to move through the structure. This might be explained by this kind of modeling. Now, so let's get back to our heart of mostly our ionic and covalent bonding types. So again, Lewis theory is going to focus on the valence electrons. So valence electrons are going to be involved in the bonding because they are the easiest to lose. And frankly, this is where we're going to see those electrons involved. So now we can either transfer or share these electrons depending on the type of bonding that's involved. Now, we say two or more atoms, right? When we talk about ionic bonding, obviously we typically deal with more than two atoms because we have these three-dimensional structures, right? In ionic bonds, one ion can make multiple ionic bonds, right? So there can be, the bond is not what we call directional. So we can get more atoms. Now, when we talk about covalent bonds, right, they're all going to be two-atom bonds, right? We're going to think of two atoms connected by a covalent bond. So we will focus on valence electrons. Lewis theory focuses on why these valence electrons are important or what they're doing. Now, so if we talk about Lewis theory in general, we start off by looking at the elements and how we would represent the elements in what's called a Lewis structure. Now, in Lewis theory, we represent the valence electrons as dots. Now, we are only going to look at main group elements here, right? So we're not looking at transition metals, right? Because we're going to be focusing primarily on, non-metal atoms. We do covalent bonding. And even if we look at ionic bonding, we're only going to focus on the early metals, right? Group 1 and group 2, and aluminum. So we represent the electrons as dots, and we can make these elemental structures or symbols based on the number of valence electrons. So the way we form them is we put a dot on each side. So we have 4 sides, and we put a dot on each side, and then we start pairing up the dots, illustrating the correct number of valence electrons. So for example, we get something like boron here, element that has 3 valence electrons being in group 3. So we're going to put 3 valence electrons on it, 1 on 3 sides. Whereas carbon in group 4 has 4 valence electrons. Remember, we can use the group on the periodic table, the main group, to predict how many valence electrons. And, we keep just going. Now, remember, when we did electron configurations, right, we can identify the valence electrons. And so, for oxygen, for example, this is its Lewis structure, right? 1s2, 2s2, 2p4, sorry, its electron configuration. We could pick out the 6 valence electrons, right? And this is really a pictorial sort of view of that, right? Where we have an oxygen showing 6 valence electrons around it. right, where we end up with 2 pairs, 2 single electrons. And we just keep going. And we get over to the noble gases here, and notice we're filled. Right? So we did a lot of talking. We talked about electron configurations of wanting to get to the electron configuration of a noble gas. Right? And when we talk about that, we refer to it as the octet rule. Right? That desire to have 8 valence electrons, to have a full s and p orbital set, to be like a noble gas. Right? We talk about it in these different ways, but ultimately we're trying to get to that octet rule. And this is going to be really a guiding principle for the Lewis structure. So as you draw Lewis structures, focusing on the octet rule is really going to be important, and it's going to help you understand why the structures are the way they are. Now, of course, the reason for this is a stable electron configuration. Right? This is going to give us the lowest potential energy structure when we can satisfy the octets of all of the atoms involved. Now, this can be accomplished by sharing or transferring, depending on if we're talking about ionic or covalent. So just remember, for transfer for an ionic bond, we share for a covalent bond. Again, we focus on 8 electrons around the atom. Now, the one notable exception here is, of course, hydrogen, which is involved in a lot of molecular compounds, so forms a lot of covalent bonds, but it cannot have 8 electrons, right? Because it only has a 1s orbital. So hydrogen will always have a duet when it's involved in bonding, so only 2 electrons. But everything else, we're going to focus on this octet rule. Now, of course, there is, of course, exceptions to the octet rule, and we'll talk about those in a section a little bit later on. All right, so this sort of wraps up our introductory period, our introductory section, and when we come back, we're going to focus on, again, a little bit more about Lewis structures, and more specifically, we're going to then take a little bit of a venture into polarity and bond polarity before we get into really drawing these Lewis structures.